Hi there, this is Savan and you're watching the Genesis YouTube channel. Today we'll be talking of a wave pulse traveling on a non-uniform string. We can observe wave motion on strings in many practical situations. For example, this shows this bow of the violin moving in this direction, and you can see that the string is oscillating in a transverse manner like this. It is this transverse oscillation that is responsible for the sound produced by the violin. As another example, look at this string in which a wave pulse is produced and it travels down the rope. It is getting reflected from the fixed end. We now go ahead with the question. A string of length L hangs vertically from one of its ends from a horizontal ceiling. The linear mass density of the string has a variable mass density given by mu is equal to mu naught x by L, where mu naught is a positive constant and x is measured along the string from its bottom end. That is, you are measuring x like this. A small transverse disturbance is produced at its lower end. This is the transverse displacement. And here the question asks us to find the time after which the disturbance will reach to the other end. So the disturbance started at this end. We have to find in what time will it reach the top end. This is the answer to the question. We now go ahead with the solution. To find the time taken by the wave pulse to travel along the string, we must first find its speed on the string. To do that, let us take a small element of length dy at a distance y from the bottom, and let us find what its weight is. Its weight will be the linear mass density at y into dy, this is the mass of the element, into g, and substituting the linear mass density as mu naught y by L, we get this expression. Therefore, we can say that the weight of the string till this cross section x will be integral of this dw, and we integrate it from 0 to x and we get this weight. Now, why did we find this weight? Because we want the tension at this cross section, because the speed of a transverse wave depends on the tension at every cross section and on the linear mass density at that cross section. A free body diagram of this x length of the string shows that the tension at this cross section x should be equal to W for equilibrium of this element. Therefore, we can write the tension Tx is equal to W, which is mu naught G by 2L into x square. This gives the speed of the wave as root over of tension at element x. You will get this value to be root over of Gx by 2. Now, one thing to observe here is that if we find the acceleration by doing dv by dt, use chain rule, first differentiate with respect to x, then x with respect to t, dx by dt, this term simply becomes v, and since v is root over of gx by 2, we substitute it back here and we get a very interesting result that the acceleration of this wave pulse is constant, which is g by 2. What was the speed at the bottommost end? At the bottommost end, x is 0. So the speed at the bottommost end from this expression is 0. So this wave pulse starts from the bottom with 0 initial velocity and it travels up with a constant acceleration like this. Therefore, the time taken to travel this whole length L is given simply by half AT square. Substitute A as G by 2 and you will get the time as 2 root under 2L by G. Now we could have found the time in a different way. If we write V as dx by dt and then separate out the variables to write it as 1 by root x dx is equal to root over of G by 2 into dt and integrate with suitable limits, you will also get the same answer. I hope you liked this question. If you learned something from it, like, subscribe, and share widely amongst your friends. And as always, till the next time, stay safe and stay healthy, you all.